Hi everyone. In this video I'm going to talk about p-values, which are one of the most important but also one of the most commonly misunderstood concepts in statistics today. Scientists use p-values to help determine the statistical significance of their results. What this means is that p-values are used to decide whether a given result is a real result or whether it's just due to chance. To calculate a p-value, you need two things. You need a hypothesis or a model, and then you need a result. The p-value tells you how probable or improbable was that result given the model or hypothesis that you started off with. In most cases, we define what's called the null hypothesis, which is our estimate of what would happen if there was nothing particularly interesting and nothing special going on, if everything that was happening was just occurring due to chance. For example, suppose we had some dice, and we weren't sure whether the dice were fair or whether the dice were biased to give sixes. In this case, the null hypothesis will be that the dice are fair. If we wanted to, we could visualize the null hypothesis as a probability distribution, here showing that the chance of getting each value, 1, 2, 3, 4, 5 or 6, is equal. Now suppose we rolled our dice and we got a 6. What was the chance of that? How unlikely was that given the null hypothesis? Well, in this case, it's very easy to see that the result had a 1 in 6 chance of happening by chance alone. Under the null hypothesis, the probability was 1 over 6, or 0.1666. If we were to roll 2 dice and take the total score across both, then under the null hypothesis, we'd see this probability distribution. If we rolled our dice and we got 2 6s, then what's the chance of that? Well, under the null, the chance is 1 over 36, or 0.02777, and so that's our p-value. That's all the p-value is. In most cases, the null hypothesis and the model associated with it is more complicated than in the example with the dice, but the principle is exactly the same. We first frame the null hypothesis, we then check our result against it to find out how likely it was under the null. For example, in many cases in science, we're interested in taking two groups of values and seeing whether there's any difference between them, whether the difference is a real difference or whether it's just due to chance sampling. In this case, I'm showing here, we've got two groups of measurements. Are they different? The values on the right look a bit higher on average than the ones on the left, but how can we be sure? It turns out there's a metric called t that we can use to help us decide. T is essentially a measure of the overlap or lack of overlap between two groups of measures. In this case, we can calculate T to be 2.603. Now, it's been shown that under the null hypothesis, that is, if the two groups of measures are actually the same, drawn from the same population, in that case, the T values will follow a T distribution, which is a particular probability distribution in which the most likely value is 0. On the other hand, if there is a real difference between the groups, the t values are likely to be higher. So we can then check our t value against the distribution to see how likely it would have been to get that value, or an even more extreme one, under the null hypothesis. In this case, it turns out that the chance would have been now at 1 in 70, or p equals 0.014, of seeing the group difference that we did by chance alone. As this p-value falls below the threshold of 0.05, or 1 over 20, it will be conventionally considered to be statistically significant. That is, it will be considered evidence to reject the null hypothesis and believe that the group differences were real and not just due to chance. But this cutoff value of 0.05 is arbitrary. It's also important to remember that under the null hypothesis, all p-values are equally likely. That means you're just as likely to get a very low p-value as you are to get a very high p-value. In fact, this is what makes a p-value a p-value. P-values are defined as values that are uniformly distributed or equally likely under the null hypothesis. Whereas, if the null hypothesis is false, p-values will tend to be low. But the fact that the p-value is low doesn't prove the null hypothesis is false. If you test the null hypothesis many times and conduct many experiments, eventually your p-value will be low just by chance. This is called the multiple comparisons problem, And in a future video, I'll be talking about that and other problems that can arise from the misuse of p-values. In general, we should remember that p-values can help guide us in determining where the truth lies, but they aren't infallible or magical numbers that we should follow slavishly. If you think back to the example of the 2 dice, the p-value from getting 2 6s on 2 dice is less than 0.05. But would you really consider that significant evidence that those dice were biased? Thanks very much for watching.